Hi, my name is Han. In this video, we're going to be talking about Cardano's formula. We're going to talk about how to use Cardano's formula in a Python script to solve for cubed roots. And then after we solve for those cubed roots, we're going to use a polynomial expression that we derived using the compressibility factor of an equation of state. And we're going to use all of the information of that to find the specific volumes if we are given a certain pressure and a certain temperature. Now I do have to mention some of the topics that I cover and go over, I go into extreme depth in some previous videos, so if you want more information on that, go ahead and look at those videos. I will be just merely glossing over and kind of reviewing the information that I've gone over before, but if you want a more elaborate explanation, then go ahead and check out those other videos. So that being said, let's get started.
So to start, we're going to go over some of the information that we have covered in some previous videos. We're going to briefly discuss them. Again, I want to say that all this information is covered in other videos in extreme depth. In this video, we're going to just briefly summarize everything so that we can kind of have a refresher as we begin to solve for the specific volumes. So to start, we have this text here that lays out the generic cubic equation of state. It goes through the different equations. It also goes and defines constants such as beta and Q and B and A, epsilon and sigma. And it goes through and it kind of just explains everything. It talks about the parameters, talks about the constants. So what we did was we used the generic equation of state and we used the compressibility factor. The compressibility factor is a factor that shows the deviation of a gas from what it would behave like if it was ideal. And so this can be defined as the compressibility factor equals pressure times specific volume divided by gas constant R times temperature. And so what we did was we put everything in terms of the compressibility factor and we took out the specific volume, and so we also used the beta and Q that is defined here in this text, and we used all this information to arrive at a final polynomial expression that has the different terms laid out. So the cubed compressibility factor terms, the squared compressibility factor terms, the compressibility factor terms, and then the constants. And so for the cubed compressibility factor, we have just one, so all we have here is the cubed. And then we have, for the compressibility factor squared terms, we have epsilon plus sigma multiplied by beta. We have negative beta and negative 1. So to clarify, these are the compressibility factor cubed terms. These are the compressibility factor squared terms. These are the compressibility factor terms. And then lastly, these are the constants. And so then we move on to the compressibility factor. We have epsilon times sigma times beta squared. We have the negative quantity of epsilon plus sigma times beta squared, the negative quantity of epsilon plus sigma times beta, and then Q times beta. And for our constants, we have negative epsilon times sigma times beta cubed, negative epsilon times sigma times beta squared, and then Q times beta squared. And so that is the final polynomial expression that we arrived at, and so we're going to be using that after we solve for the cubed roots to determine what these specific volumes are at a given pressure and a given temperature. So moving on, we are going to talk a little bit about Cardano's method. So Cardano's formula is a formula that was developed to figure out what the cubed roots of a polynomial expression are. And this formula is for any polynomial expression that is in the form ax cubed plus bx squared plus cx plus d, and that is assuming that a is not equal to 0. And so for the polynomial expression that we arrived at using the equation of state, we assume that a is equal to 1. And so we have this cubic equation here on the left, which is what we have up here on top. And so what we are going to do for Cardano's method is we're going to solve for Q and R, and then we're going to use that information to solve for theta, and then if R squared is less than Q cubed, we will solve for theta, and then we will use that Q, R, and theta value to solve for the roots. So this is the kind of first possibility that comes with it. Now, if the r squared minus q cubed is not, or r squared is not less than q cubed, what's going to happen is we are going to have to move on down to here. So essentially what this text is saying is that these two equations is going to form this equation down here. And then based on the b value, so we have an a value and a b value, based on the a or b value, we will then use that information to solve for the cubed roots down here. So this is the kind of second route that could go. So Cardano's formula has two different, it kind of has an if situation, and it splits into two different versions based on what the solved for q and r values are. So the next thing that we're going to review very quickly is some code that we wrote in this video, that in a previous video, that just kind of is information that we're going to be using in this next Python script. So I want to make sure that I go over that so briefly so that we can know exactly what everything means. And so in this previous script, what we did was, the first thing that we did was we imported some tools, and so we used this !get clone and this URL that is a previously developed Python script that basically has a lot of properties of different substances. We used it for our water properties, and then we imported sys, which allows us to find the information very quickly, and then we imported the tools that is from this URL as che. We imported numpy, which allows us to do a lot of mathematical functions like logs and sorting and a ton of other things, but it's just a wonderful mathematical tool. We also, from SciPy Optimize, we imported roots. This allows us to solve for roots. And then we also imported subplots. This allowed us to make a plot that showed different isotherms. We do this in the previous video. And then we defined some constants. We defined the gas constant R, and then we also defined P, which is when we refer to water properties. And this is the really important thing that we're going to be using in our script in this video, is we wrote out a function to solve for the A, B, epsilon, and sigma constants of the van der Waals or SRK equations of states. So what we did was we used the text that we were given above, and how we went about doing it was we used this chart here as well as this information that we are given on how to solve for B and how to solve for A, and we plugged that information in. So we wanted to solve down here. We knew that we wanted to solve for the constants, and so we slowly defined the constants one by one. So we defined that the constant B is omega times the gas constant R times the critical temperature divided by the critical pressure, and then we had to then define omega. So for van der Waals equation, omega is 1 divided by 8. For SRK, we know that omega is 0.08664, and then we went on to define epsilon and sigma, because these are pretty easy. There were no equation, so we just know that for epsilon, van der Waals is 0 and SRK is 0. For sigma, van der Waals is 0 and SRK is 1. And then we went on to define A, which was slightly more complicated. It was this equation that is psi multiplied by alpha multiplied by the gas constant R squared times the critical temperature squared divided by the critical pressure. And then so we had to define both psi and alpha. So psi for van der Waals equation is 27 divided by 64. For SRK it is 0.42748. And then alpha for van der Waals is just 1, and SRK is this long equation. It is 1 plus the quantity of 0.480 plus 1.574 multiplied by a property of water that is called the eccentric factor, which is just a factor that accounts for how molecules are not perfectly sphere. Anyways, it was 1.574 multiplied by the eccentric factor minus 0.176 multiplied by the eccentric factor squared times 1 minus the reduced temperature to the 1/2, and all of this whole quantity was squared. The reduced temperature, or any reduced term like reduced pressure, reduced volume, reduced temperature, it is just the temperature divided by the critical temperature. So for pressure, it would be the pressure divided by the critical pressure. And as you can see, we had all of these in squiggly brackets, and then we had EOS and brackets at the end. EOS is what we named the equation of state dictionary. So whenever we wanted to, let's say, use this to solve for van der Waals, we would just change this to VDW, which stands for van der Waals, and then it would solve for the roots, or for the constants, excuse me. It would solve for A, B, epsilon, and sigma, the constants, using van der Waals equation of state. But right now, we want to find it using SRK. So this was used to find the constants. We will be using the function cubic ABES to solve for the constants later on in this Python script that we will write on down here. So before we move forward, we're going to kind of write out the steps of how we want to go about writing this Python script, and then we're going to head on over to Python and actually write it. So the first thing that we have to do is we have to solve, so the first kind of major step is we have to solve for cubed roots. And we're going to use this, so this is why we talked about Cardano's formula, because this is going to come into play. So to solve for the cubed roots, what we're going to actually do is these are kind of the list of how you would go from start to end. So what we're actually going to do is we're going to work backwards. So what we want to find for this second version, so this is for second. So for the second option, what we want to do is we want to find this value here for the roots. And so that's going to be x equals a plus b minus a over 3. And then so what we're going to do is, in order to solve for b, we have to either do q over a or 0. And then to solve for a, we have the negative sign of r multiplied by the quantity of the absolute value of the gas constant r plus the square root of r squared minus q cubed, all to the 1/3 power. And then how we go about defining that is if r squared is not less than q cubed. So that's for the second option that we have in Cardano's formula. For the first option, we have these formulas for the cubed roots, and so I'm not going to write those out, but that would be what we would do first. And then in order to do that, we would have to find what theta is. So after we do that, we would find theta, which is r cosine r divided by the square root of q cubed. And then to find theta, what we would have to do is, or that was to find theta. To find r, we would have to do 2a cubed minus 9ab plus 27c divided by 54. And then to find q, we would have to do a squared minus 3b divided by 9. And to know that we would do this, this is when r squared is less than q cubed. So the first thing we would have to do before everything is find this r and q value. So that's pretty much what our code is going to look like. We just want to work backwards because we know what we are looking for. We have to find what is unknown in each step. So we know that we are looking for this root. We don't know b and a, so then we have to find the unknowns, and then from there we find the unknowns in there. So it's kind of a domino ripple effect. So that's the first step, is we want to solve for cubed roots. Now the second step that we have to do after we solve for the cubed roots is we have to solve for the specific volumes. So the first thing that we're going to do when we solve for the specific volumes is we have this giant polynomial equation here, and so we know that we want to solve for V1, V2, and V3, which is the 3 specific volumes. And then how we want to do that is we are going to use the compressibility factor that we defined up here. So we know that Z equals pressure times, so compressibility factor equals pressure times specific volume divided by gas constant R times temperature. So we know that over here we know that compressibility factor equals pressure times specific volume divided by gas constant R times temperature. So then we can use algebra to manipulate this equation. So we know that specific volume equals the gas constant, or compressibility factors times the gas constant R times temperature divided by pressure. And then so we know that to solve for each of these, what we have to do is we have to do the compressibility factor times P pressure, or R, gas constant R times temperature divided by T pressure. And then so we are given the pressure, we are given the temperature, so all we have to do is find the compressibility factor. And so in order to find the compressibility factor, we are going to use this giant polynomial here. We know, I'm not going to rewrite this whole formula, but we know what the formula is, and in the formula there is something called beta and something called Q. And so we're going to use the information that we are given in the text up here to solve for beta and Q. And then we know that in beta and Q there are constants A, B, and epsilon and sigma. And so in order to solve for that, we're going to use the Python script that we mentioned earlier in this video that solves for the constants A, B, epsilon, and sigma. And once we plug that all in, we will end up with our volumes. So that was a quick overview of the steps. Now we're going to head on over to Python and actually code it out and figure out what these specific volumes for a given pressure and a given temperature are. So now that we have A defined, we want to move on to define B. Now defining B is a little trickier because there's two options. B can either equal Q divided by A if A does not equal 0, or B can equal 0 if A equals 0. So similar to how we did the if-else with the r squared less than q cubed, we're going to use an if-else statement. We're going to use it a little differently. With the r squared, we did if r squared is less than q cubed, then so-and-so, or else so-and-so. Now we're going to actually do it the opposite version, and we're going to do b equals so-and-so if so-and-so, or else so-and-so. That sounded very confusing with all the so-and-sos, so let me code it out and show you what it's going to look like. So we're just going to make a broad statement that b equals 0. But that's not completely true, because b only equals 0 if a equals 0. So what we have to do is we do if a, and we're going to use two equal signs because this is a conditional statement. We're not naming a, we're not saying that a equals 0, we're saying if a equals 0. But if not, so else, if anything else, then b is going to equal q divided by a. Plain and simple. So if we were to read it like a sentence, it would be b equals 0 if a equals 0, or else q divided by a. So we have a, we have b, we have everything defined that we need to find. So we're going to shift enter. There's no immediate errors. we're going to go on and code the second function, and if there's an error after that, it will let us know. For right now, it looks good, so we're going to move on. So we have done this blue step here, the blue first step, which is writing out a function that will solve for the cubed roots using Cardano's formula. So now we're going to use those cubed roots in just a moment, but we're going to use it to solve for the specific volumes. So we know we're going to say that this function, we want to use a function that will solve for the specific volume, so we'll call it cubic SV, and we want to give it some parameters, give it some things that we have. And so we know that we are going to be given a pressure. We're going to be given a temperature, and we know the equation of states that we're going to be using for this is the SRK. So those are the information that we are provided in the question. And it's saying solve for specific volumes when you are given a pressure, when you are given a temperature, and it is in the equation state of SRK. So that's what we are given. We want to return. So what we want to get out of this is we want the specific volumes. So we want V1, V2, V3, but we don't really know what they are necessarily, but we do know that the specific volume equals the compressibility factor multiplied by the gas constant R multiplied by temperature divided by pressure. So that's what we're going to put in, because that's the formula we have for what specific volume is. So we are going to put in the compressibility factor multiplied by the gas constant R multiplied by the temperature divided by the pressure. So now we have to go on and define what the compressibility factor is, because we haven't defined what that is yet. So this is when the polynomial equation that we derived in the previous video and that we went over at the beginning of this video comes into play. So this is how we are going to solve for what the compressibility factor is, or at least tell Python what the compressibility factor is. And so for a cubic equation, we have x cubed plus ax squared plus bx plus c. So the a, b, and c are the cubed roots that we solve for using our cube roots function. And so we don't have what a, b, c are. We don't know what the values are, but we have a function that solves for it. So we know that it's going to use the function cube roots. And the cube roots are going to give us an array that is the first root, which is A, the second root, which is B, and the third root, which is C. And we can look at this cubic equation and know that, well, the A value is going to go with any term that is x squared, or in our case, compressibility factor squared. We know that the B term is going to go with any term that is x, or in our case, compressibility factor. We know the C value is for the constants. And so we're going to input it in that exact order. We're going to input the Z compressibility factor squared, and then we're going to input the compressibility factor, and then we're going to input the constant. So we're going to start here. We know that the cube roots is going to solve for that. And so the first thing we have is the compressibility factor squared, which is going to line up with this first value A here. And so the term for that is epsilon, which we have defined as E, plus sigma, which we have defined as S, multiplied by beta, multiplied by the compressibility factor Z squared, which we are solving for, so we don't put that into the equation. We just know that that's going to be there. So essentially we're following this chart, but we're going to do it following the equation so we can see it. And then we have minus the beta, and then we have minus 1, which is just the compressibility factor, Z squared. So that is all of our terms for the A root. And then moving on, we have the B roots, which is just compressibility factor. And so the first one that we have for that is epsilon multiplied by sigma multiplied by beta squared. And then we have minus the quantity epsilon plus sigma multiplied by beta squared. And then we have minus the quantity epsilon plus sigma multiplied by beta. And then we have our last quantity, which is just Q. And so that is all of our terms for the root B. Now we move on to our last, which is the constants for the root C. So we have negative epsilon times sigma times beta cubed. And then we have minus epsilon times sigma times beta squared. And then we have plus Q times beta squared. And so those are all of our terms for the different cube roots. So we have the term A, all the terms that go with A, all the terms that go with B, and all the terms that go with C. So we have that put in. So these are all the terms that go with A, all the terms that go with B, and all the terms that go with C. And so now we are going to move on and define all the constants in this polynomial that we have yet to define. So first we have beta. So if we look at the text that we are given, we know that beta equals B constant times pressure divided by gas constant R times temperature. So we're going to put that in. So we have B times pressure divided by the gas constant R multiplied by temperature. And then so we have B defined. Now we are going to move on and define Q. So Q over here we have is the constant A divided by the constant B times the gas constant R times temperature. So we're going to put that in. We're going to do A multiplied or divided by B times the gas constant R times temperature. So now we have the constants A, B, E, and E is for epsilon and S for sigma that are undefined. Well, as we mentioned at the beginning of the video, we have a function already written out to solve for these constants, and we have it defined as cubic ABES. And so that's exactly what we're going to do, is we're just going to put in the fact that we know that A, B, E, epsilon, and S, sigma, is equal to the cubic ABS function at a specific temperature and for the equation of state of SRK. So now when we have everything defined, we're going to shift enter. And it looks like everything is working. So let's try it out. Let's say we have a given temperature and a given pressure. So we're going to use cubic SB. We're going to find the specific volume at a given pressure. Let's say at 1 times 10 to the 7th pascals and at a given temperature of 300. We're going to shift enter. So as you can see, we got a specific volume. The only issue is we know that when we look at a PV diagram, there's going to be 3 points for the specific volume because it does like a curve. And so there is something wrong with our code, which is okay, mistakes happen. So we're going to go back and see where we can find this error. So one of the first situations is we want to go back to this cube roots, the first step, and see if there's any error in what we did. It happens to be an error here, as we want 3/2 to be what Q is to the power of, not to 3 and then do that divided by 2. So we're going to change that and make sure that that's in parentheses. Another error that could be why we are not getting 3 values is because this return here, Python may not know it may return all 3, but it may not return in the correct order. So what we're going to do is we're going to give this the name roots, and we're going to actually return the sorted roots. So not just the roots, we're not just going to return the roots like we did previously, but we're going to return the sorted roots, so np.sort roots. Okay, so we're going to shift enter all the way through and see if that solves our issue. It does not. So there's another issue somewhere, and so we're going to go through and see if we can find it. So first, let's look at our roots equations. Let's see if we followed those correctly. So this last root here, there should be beta minus 2 pi divided by 3. So we're going to go back and fix that because we did not include the divided by 3. Now we're going to shift enter to see if that fixed our issue. It did not, so we're going to keep looking through. The A values and B values match here. So we're going to move on to the cubic equation and see if we missed something in that. So we're going to work backwards like we did earlier, and we're going to have this, which is the correct formula for how to find the specific volume with the compressibility factor. So we're going to move on. We're going to look at the polynomials and the roots that we put in. So we're going to find the cubic roots. So we have epsilon plus sigma times beta. Then we have minus beta minus 1. For the b values, we have epsilon times sigma times beta squared minus epsilon plus sigma times beta squared minus epsilon plus sigma times beta plus q times beta squared. Oh, we only have q. Epsilon plus sigma times beta and then plus q times beta. But here, either way, we only have q, so we need to add the beta. And previously, when I was troubleshooting, I noticed that we have a b value determined here, and then we named the same value b down here. So I just changed all of the b's down here to betas. This is to make sure that there's no confusion between the different b's, and it makes it a little easier when you're reading the code that you know that this is beta while this is the b value for the cubed roots. Yes, they're different functions. They probably will not correlate with one another, or Python will not get the two confused. But for our sake, it makes our life a little easier when we're reading the code. So all these have been changed to beta. So previously they were just b's. But now we have beta. So they looked like this before, and now they look like this. So we're going to keep checking just to make sure the rest of this is right. So we have negative epsilon times sigma times beta cubed minus negative epsilon times sigma times beta squared, and then q times beta squared. So we're going to shift enter to see if that fixed our issue. It did not, as we still only have one root. So there is something else that is incorrect. So we're going to go back and see if we can find that issue. So in seeing that these numbers are negative, I realized that even though I now have 3 specific volume values, there is an error somewhere in the code. So I decided to go back and see where my mistake was. So I looked at this 1/3 here and realized that maybe it could possibly be the parentheses. So I went and changed that. I still have a negative value and the values are still incorrect. So I went back even further to the equation that I had, and previously I had it like this. So what had happened was when I had went to copy this negative q times beta squared into my chart, I had left out the negative sign. So this is actually a negative q beta squared, and so this would be minus. And so if I were to change that in my function, and I do minus, and I shift enter, that gives me the correct positive values for the cubic equation of state. So these are the correct specific volume values. And so that script here is how we use Cardano's formula to solve for the specific volume if we are given a pressure and a temperature.